This one's too hot. This one's too cold. And this one's just right. But what is just right when you are looking for a star that can support life? You need longevity, stability, and a dash of metals. Hi, I'm Dave Dooling at the New Mexico Museum of Space History. A favorite part of sci-fi movies is starships finding habitable worlds orbiting just about every star. With more than 300 billion stars in our galaxy, something should be out there. But which ones? First, you want a star with a good Goldilocks zone for planets. Not too hot, not too cold, just right. And it's more than orbiting a star at the right distance. You want a broad, continuously habitable zone, an idea developed in the 1990s by Dr. James Casting of Pennsylvania State University. An infinite universe may allow an infinite range of chemistries, but the betting money looks for what we know works. Casting used liquid water as its basic criterion. The planet has to be between boiling and freezing to have life as we know it. It's easy to calculate how far away you should be to get the right amount of sunlight. But stars become brighter as they age, meaning that the Goldilocks zone evolves too. That brings us to the Hertzsprung-Russell diagram developed in 1910 by Einar Hertzsprung of Denmark and Henry Norris Russell of the United States. It plots star brightness against temperature. This is where we get the famous main sequence often mentioned in sci-fi stories. It's the diagonal band where stars spend most of their lives as they fuse hydrogen into helium. The lettering on the HR diagram's horizontal axis was worked out by Annie Jump Cannon, a pioneering American astronomer in the early 20th century. Cannon discovered that the original A-B-C-D classification of star colors was wrong. Bluer stars are hottest and red the coolest. Cannon rearranged the old designations into the modern sequence, OBAFGKM, to match dropping temperatures. To help students remember this, Cannon coined the expression, "Oh, be a fine girl, kiss me." A few years later, Hertzsprung and Norris used it as the x-axis in their diagram. Unknown at the time was how the mass of stars controls their lifespans. Massive stars live fast, die young, and leave a pulsating corpse, a black hole or a neutron star. They burn through fuel in a few tens or hundreds of millions of years, much faster than life can get a toehold and exit the main sequence with a bang, after they sterilize their solar system. All stars bloat with age. Bigger surface area makes them brighter even though the surface temperature stays about the same. That means the Goldilocks zone moves outwards with time. The brighter the star, the faster the zone moves outward and the less time that life has to evolve. So to find a star that lives long enough to support advanced life, Casting's idea of the continuously habitable zone, we need to skip past the O, B, A, and F spectral classes. With a nod to Cannon and her work, I use the phrase, Goldilocks, kiss me, because G, K, and M stars are the best bets for finding life. Their colors fade from yellow to orange to red, with 10 steps within each color. Our Sun is a spectral G, step 2 main sequence, represented by the Roman numeral 5, so it's often called a G2V. It is about 4.5 billion years old and has another 5 billion left before becoming a red giant that bakes Earth and then becomes a white dwarf. Our Sun's Goldilocks zone is slowly working its way outward, and the inner edge will reach us in about a billion years. By then, the Sun's rising luminosity will boil the oceans away. Want more time? Try an orange K-star. K-stars are less luminous than our G-star, so the Goldilocks zone is closer and smaller. But it evolves more slowly and may last up to 40 billion years. Our galaxy has about 3 times more K-stars than G. Fainter still are M stars, red dwarfs. These weigh less than a third as much as our Sun, may live 100 billion years, and make up about half the stars in the galaxy. Even more chances to find life? Maybe, maybe not. Small stars convect from center to surface, leading to massive flares and X-ray bursts. K-stars produce 25 times as much X-ray radiation as our Sun, and M-stars produce up to 400 times as much. But there's a literal sliver of hope. Because M-stars are faint and age slowly, their Goldilocks zones are very small and stable. Planets that close are tidally locked with their stars, like our Moon with Earth, so one side always faces the star. The sunny side may be baked dry and zapped by X-rays, while the night side is under permanent ice. But life may be possible in a twilight zone with the red star just on the horizon, or possibly under the ice. The discoveries of life at the bottom of Earth's oceans and of water inside icy moons around Jupiter and Saturn opened new possibilities for looking for life beyond Earth. Finally, the star must have enough chemicals to make planets. Astronomers call this metallicity, although it means anything heavier than the hydrogen and helium that make up most stars. Unless the cloud that gave birth to the star had the rest of the periodic table of elements, you can't build planets and life. So how many HAB stars, habitat supporting stars, are near us? In 2002, Dr. Margaret Turnbull at the University of Arizona searched more than 100,000 stars studied by the Hipparcos Space Telescope and produced a catalog of nearby habitable systems. Turnbull's criteria were that a star had to be at least 3 billion years old, so she included late F stars. It has to be non-variable and long-lived, so it has a good habitable zone, and have good metallicity, so it can build planets. After applying those and other filters, Turnbull had 17,129 candidates, about 1 in 7 surveyed by Hipparcos within a few hundred light years of Earth. Most are F and G stars. The survey has fewer K and M stars because they are also the faintest stars and harder to detect. But the 25 closest HAB star candidates, all within 80 light years of Earth, are each a type G star, and 8 are near twins of our Sun. Finally, Turnbull admits her catalog is just a start. She noted that, despite the broad array of data used to assemble this catalog, this exercise has forced us at every turn to admit that we are defining habitability from a position of considerable ignorance. A complete characterization of all nearby stars is simply not realizable at this time. Still, 17,000 stars are enough to keep us busy for a long time. And how about the thousands of exoplanets we have found? That's another story for another day. Thanks for watching, and stay tuned for more stories from space.